what is an oxidizing agent? In fact, I'll do it over here because that way I've got room. What is an oxidizing agent? Something that helps another thing to oxidize by taking electrons. Yes, that is absolutely correct. An oxidizing agent oxidizes the other guy. By taking electrons. And if it's taking electrons, if the oxidizing agent is taking the electrons, that means that the oxidizing agent will be gaining electrons. So the oxidizing agent actually ends up getting reduced. Okay, so we're going to be looking at these in more depth today. And of course, the reducing agent is the opposite of that. And we're going to look at this little activity here, and I will post this in the assignment section so you can go through it yourself later and see if you can fill it in the same way we're filling it in now. Don't worry about trying to fill anything in at this point. But this is an activity I would normally have you do in little groups, but we're going to just do it as a class. So why are we doing this? One of the chemical properties of metals is that they form cations in chemical reactions. This requires them to lose their electrons or become oxidized. So metals lose their electrons and they get oxidized. If they're getting oxidized, what kind of an agent would they be? If those metals, for example, magnesium, solid, etc., if they are getting oxidized, are they oxidizing agents or are they reducing agents? Yeah, they're reducing agents. Sorry, I was just having a problem with my chat. You guys have been answering me and I haven't been seeing it. Yeah, so they are reducing agents. Therefore, metals. And when I say metals, I don't mean metal ions. Okay, so this is metals, not metal ions. Are reducing agents. Reducing agents. So we're going to be using that language as we move through here today. And so the electrons from the things that are being oxidized, those metals, they need to go somewhere. And so some metals will tend to stay in their neutral state. And we're going to figure out which metals are better at making cations and which ones are better at staying neutral. So who likes grabbing electrons more? So we have, in model 1, we have some metals here. And what you can see is I have taken a strip of magnesium here, okay, and I have dipped it into a solution of zinc 2+. Okay, the font's a little small there, so I'll just, that's zinc 2+ solution. And when I do that, you would see there would be a black coating on the outside of the magnesium metal, which is where some zinc actually plated onto the metal. And instead of now having zinc 2+ in solution, you will now have magnesium 2+ in solution. Okay, so a reaction occurred here. Yes, a reaction occurred. Let's find one where a reaction doesn't occur, just so we can take a look at that. If I can make this the right size. There we go. Oh, look at the one right below it. Look at D here. Here we have aluminum and we've stuck an aluminum strip inside a solution that contains magnesium ions. What happened when I left it for a while? Guess what? Absolutely nothing. Okay, so absolutely nothing happened. So there was no reaction here, no reaction. And if we were here and we were in person, you would be doing this lab, but we're just going to look at little pictures of it. There used to be a fantastic simulation, but it requires Flash, and nobody supports Flash anymore, so we can't look at it. Okay, so this is the model that we're going to look at. Please note we have left out water molecules and spectator ions, just for ease of analysis. Okay. Which ions, sodium or nitrate, are more likely to be the missing spectators in the beakers of Model 1? Okay, so we've left out the spectator ions. Let's take a look at our beakers. Our beakers contain zinc 2+ in solution. They contain magnesium 2+. They contain aluminum 3+, magnesium 2+, copper 2+. Is my spectator that's not been shown, spectator, more likely to be sodium, or is it more likely to be NO3-? Is my spectator more likely to be sodium plus, or is it more likely to be nitrate? So if I wanted to have, say, copper 2+ ions, who would be paired up with it as a spectator ion? Seriously? Nobody? So, okay, let's put it a different way. When I dissolved my copper 2+ into solution, was it put in there as copper Na, or was it put in there as copper NO3? What do you think? NO3. It has to be the copper NO3 because we're dealing with the copper ion, so it needed to have an anion with it. Sodium couldn't be the spectator ion because it wouldn't be partnered with copper or magnesium or aluminum. Those are all cations. They would need to be partnered with an anion. Okay, let's try our next question here. List 2 pieces of evidence from experiment A in Model 1 that indicate that a reaction has occurred. Well, that's pretty easy. What indicates that a reaction has occurred? Well, we started with no blob of zinc. There was no blob of zinc over here on the magnesium, and we finished with a blob of zinc. So no blob of zinc, and then we finished with a blob of zinc. Can anyone see a second piece of evidence that a reaction has occurred here? What's a second piece of evidence that a reaction has taken place? Yeah, we now have magnesium solution. We used to have zinc, and now we have magnesium. Okay, good stuff. All right, next question. List 2 pieces of evidence from experiment G that indicate that no reaction has occurred. Well, I think that's a stupid question because it's like, well, nothing happened. There was nothing and there was nothing. It was exactly the same as before. So we're not even going to bother with that one. Question number 3. Circle the letter below each experiment that resulted in a reaction. Okay, so let's go back here, and I'm going to get rid of all my stuff here. And you guys are going to, for yourself on a piece of paper just near you, you're going to say to yourself, should I circle A, should I circle B, should I circle C? Should I circle A, should I circle B, should I circle C? Did a reaction happen? In A, was there a reaction? In A, was there a reaction? Yes, there was. Okay, so we can circle A. And in B, there was a reaction because we see, again, we have new stuff, right? Oh, there was aluminum when there wasn't, and there used to be aluminum 3+, and now we have magnesium 2+. And so we can go through and say, oh my gosh, look at this one even went from being blue to being colorless. That's pretty exciting. And remember, copper metal isn't like a silvery color, it's a copper color. So we definitely had something happen there. Now, how about the rest of them? Well, D, we did not have a reaction. We decided on that. E, oh, looks like something happened there. We got zinc plated on top. F, definitely, we went from having copper 2+, which is blue. Just in case you ever need to know, copper 2 is blue. It rhymes. Okay, and oh, no reactions in G, H, or I. Everything just sits there, the same before as afterwards. You can see if we get up close that we started with magnesium and we finished with magnesium. We started with aluminum, we finished with aluminum. There's nothing new. Okay. All right. We're going to write single replacement reactions under each of the beakers to illustrate the reaction. Okay, let's do that. So if we write a single replacement reaction here for this beaker A, our reactants are, well, we're starting with magnesium and we're starting with zinc, so we would write Mg plus Zn 2+. Who are the products of that single replacement reaction going to be? Who are the products of that single replacement reaction going to be? Who are the products? I started with magnesium solid, right? That's our magnesium. It's a solid strip. And I started with zinc 2+, aqueous. Who am I finishing with after the reaction? What new things did I get? Yeah, I got zinc. Okay. Now, what's the charge of that zinc? If you look at it here, it's a solid. And you remember, any element in its elemental form okay, so not in a compound, has a net charge of 0. So the oxidation number of that zinc is 0. So this is going to be zinc 0. And in fact, we started with magnesium over here in its elemental state. So that was magnesium 0. Okay, and that is zinc solid. We actually have some solid zinc forming on the outside of the magnesium strip. And in the solution, we now have Mg2+ ions, Mg2+. And that will be aqueous now, okay? And we can do the same thing for B, okay? So we have Mg is a reactant. That's our solid. And our other reactant is the Al3+, Al3+ aqueous, goes to, and we're going to end up with over here, what are the two new things that we made in this reaction? What did we make in this reaction? Yeah, we made aluminum neutral, and it's a solid, and we made magnesium 2+. Okay, I'm not going to write each and every one of these reactions. When I assign it to you, you can go through and do the rest of them. They'll just be exactly the same. I want to know why that stupid thing keeps going, but okay, whatever. Okay, next question. Here we go. Circle the species in each of the reactant beakers that underwent oxidation. Okay, so let's go back here and let's do A and B. And so we're going to circle the species that underwent oxidation. So I'm going to get rid of all my circles because that's, you know, I've circled everything. So who has undergone oxidation in this beaker here? Who undergoes oxidation in this beaker? Actually, I should put it here because it's the reactants that either undergo oxidation or reduction. Is it the magnesium or is it the Zn2+? Who is undergoing oxidation? Magnesium or zinc? Yeah, it's that magnesium, okay? It's going from 0 to 2+. So it must have lost 2 electrons. So when you're going through this, you're going to say, okay, I can identify that magnesium underwent oxidation. Okay, in my second beaker, in beaker B, I can say, oh, who underwent oxidation? Well, it's the same thing. I went from magnesium 0 to magnesium 2+. So again, the magnesium underwent oxidation. So that's what you'll be doing for that question. Okay. Draw an arrow from one species in each of the reactant beakers to another species in each of the reactant beaker to show how the electrons were transferred. Aha. So we are going to be drawing an arrow. Either we're going to draw an arrow from magnesium to zinc, or we're going to draw an arrow from zinc to magnesium to show that that's the direction of electron transfer. Which one is the correct option? Is it A, zinc to magnesium, or B, magnesium to zinc? Which one is the correct direction of electron transfer? Magnesium to zinc. Yes, absolutely it is. Okay, so it's going from magnesium to zinc. So that's going to be that one. So that's what you're going to do for that question, is you're going to say, this guy got oxidized, and so it transferred electrons to the zinc. This guy got oxidized, and so it transferred electrons to aluminum. Okay. Ay, ay, ay. Things driving me crazy. Okay. There we go. Find the 2 experiments in Model 1 that involve aluminum and magnesium. So we're going to go back and do that in a minute. Will aluminum give its electrons to magnesium? Will magnesium give its electrons to aluminum? And then we're going to answer which metal is better at giving up electrons. So Will aluminum give them to magnesium? Let's see, here's our aluminum magnesium beaker. Come back. Okay. So the question was, will magnesium give electrons to aluminum? And the answer is yes. Okay, magnesium is giving electrons to the aluminum. What do you predict is going to happen if I have a stick of magnesium, or sorry, a stick of aluminum now in a magnesium solution? Will aluminum give its electrons to magnesium? Will aluminum give electrons to magnesium? What do you predict is going to happen? Before I scroll down and take a look at it, what do you predict will happen? Will aluminum give its electrons to magnesium? What do you predict? Magnesium will give to aluminum. Will aluminum give to magnesium? All right, let's find out. Because you guys are just guessing at this point, right? Be brave, take a guess. Let's take a look and see what we have with aluminum and magnesium. Oh my goodness, here we are right here. Here we've got it reversed. In the other one, we had magnesium up here and aluminum down here, but in this case, we've got aluminum as the metal and magnesium down below, and lo and behold, there is no reaction. Okay? And if we were to take a look at any of the other pairs, okay, so if we were to look at, let's see, we have magnesium will give electrons to zinc. So magnesium 0 will give electrons to zinc 2+, right? That's what we're seeing here. Okay, and we end up with zinc 0 and Mg2+. Do you think will zinc 0 give electrons to magnesium 2+? Will zinc 0 give electrons to magnesium? If magnesium will give to zinc, will zinc give to magnesium? You guys are killing me today. Okay, let's go back here and remind ourselves. And if you're like, I don't need reminding, then you need to start answering some questions, okay? Will magnesium give to aluminum? And the answer was yes. And then we said, will aluminum give to magnesium? And then the answer was no. So when we went backwards, the answer was, if the answer in forward was yes, then the answer in the verse was no. So over here, if we said yes, magnesium will give to zinc, then the answer, will zinc give to magnesium? The answer has to be no. And let's go and see if we have that here. Did they give us one of those? They didn't. Oh my God, well, that really sucks. But anyway, that's how it should work. That is how it should work, okay? And if life was just, they would have given us that combination of metals as well. Did they really not give it to us? Yeah, they really didn't. Those buggers. Oh well. Okay. So let's see. Will aluminum give its electrons to copper? Will copper give its electrons to aluminum? I'm going to let you guys do this, okay, on your own, because you have now seen how it is done. predict what might happen if you put a piece of metal in a solution of its own ion. So let's say we put copper metal, okay, Cu2+, there we go. Do you think there would be a reaction? Do you think there would be a reaction if we put copper into a solution of copper 2+? No, because really, not much is going to happen there, right? There's copper 2+, the electrons don't really care, okay? So what this means is that out of every pair of metals and metal ions, one of them is better at pulling electrons towards itself. So if we are to look at our magnesium aluminum example, aluminum is better at pulling electrons. It is better at gaining electrons than magnesium is, because when we did the same reaction the other way around, magnesium 2+ was not able to gain those electrons. So if I said aluminum 3+ is better than Mg2+ at gaining electrons, what process is aluminum better at? Therefore, aluminum 3+ is better at getting what? Oxidized or reduced? Is aluminum better at getting oxidized, or is aluminum better at getting reduced? Yeah, it's better at getting reduced. And this tells you that aluminum is a better what kind of agent? Aluminum is a better, oops, something or other agent. What kind of agent are we talking about there? Yeah, it is a better oxidizing agent. Okay, so it's better at pulling electrons away from that other guy. All right, and you can do a series of experiments and you can compare them one with the other. And next class, I'm going to give you some data from a lab that we would have done, and we can make our own little list of who is stronger than whom, okay? All right, but while we wait for that, let's see if we have a few more questions to answer here. Blah, 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 blah. An active metal readily gives up its electrons and is oxidized. There are 4 metals involved in this reaction. There is magnesium, there is aluminum, there is copper, and there is zinc, okay? And we're going to rank these. Who is better at giving away, who is best at giving electrons? And if it's giving electrons, that's the same as losing electrons, right? Which means that these guys here would all be what kind of agents? Yeah, these guys are going to be who is the best, if they are, who is the best at giving electrons, who's the best at losing electrons. This is going to be who is the best reducing agent, because remember, if you are losing electrons, if you are getting oxidized, you are the guy who is reducing the other one. You're reducing your partner, okay? If I am losing electrons, I am giving them to someone else and that other person is gaining them. And that means that I have reduced that other guy. So I am the reducing agent if I am getting rid of my electrons. Okay, so I will have you try that one on your own. We'll go over that one next day. Okay, and then you're going to, oh yeah, you can do number 8. And you can do number 9, I think. Can you do number 10? Okay. Yep. You could do number 10. And then we might just stop. Okay, so why don't we call that a day, and you're going to, oh, we'll do up to number 11. Look where it says stop.